Now we're going to discuss the indirect boundary element method. This is different than the direct boundary element method. It's still valid for these infinite regions, so it's useful for a body that might be open to the exterior field. But it also is useful for some other interesting geometries, such as a fin that's radiating noise. Something like a cooling fin on an engine might also be an acoustic source. And how to handle that free edge is important and can be done here. Generally speaking, the indirect method considers the fluid on both sides of some boundary, and that's what allows the generality. You end up with symmetric equations. It's a more powerful method. It lets you solve transmission of noise through elastic bodies, the so-called transmission problem. So there's, or transmissibility problem. So it's a nice method. It's very powerful. The theory is a little bit complicated, and we're going to outline it pretty much up to the end where the variation is to be done. So I think for the average viewer, you want to pay attention and understand that there's quite a strong theory involved here and that it's been done properly. And I'd like you to understand as much of the detail as you can without getting bogged down. So I'll go through some of the theoretical points here on our first slide. The fundamental solution, which would be the same as for the direct method. We do some volume integrations. We do it in a little bit different way this time by talking about what are called boundary variables. And these are jumps in pressures and velocities rather than those variables themselves. So you're getting a difference in a quantity across a boundary. We'll go through the discretization process and look at the variational process that ends up with the final matrix equations. Something new is the so-called constraint equation that's needed at the free edge, cut edge of a fin perhaps. Also, when you have multiple structural surfaces coming together, you get these constraint equations needed to relate that multiple intersection. Lastly, as in the direct method, you have to recover the pressure at some data recovery point, and that's done with a given equation. Okay, let's start on our theory. We'll start with the general concept of a vibrating body. This body has a surface which is moving harmonically in time, and we might be interested either in the interior problem or the exterior problem. So I've shown a cross-section of this vibrating body. It's like a hollow potato. We'll use a vector system for positioning with the heavy character R as a vector from some reference point to perhaps a point on the vibrating shell, or perhaps a point at a so-called data recovery position. You might think of this first position as a source, and then the second position as a point where you are listening to hear the sound. Interestingly, by the time we get done with our discretization, we're going to put the data recovery points back on the surface for our first solution to get n equations and n unknowns. And so those 2 points might coincide at times. There is a mathematical singularity involved, which makes that a little bit more creative than you might think, because the source, a point source of sound, is similar to pressure point sources in aerodynamics and electromagnetic point sources, where you get a potential singularity there. So that has to be properly handled when that time comes. And when the viewing point then is moved to be coincident with a source point, you have to be a little careful how you handle that. We will later then view this surface as a collection of point acoustic sources spread around the surface in some logical way to describe the surface. Our sound recovery point out here, and remembering that you could either be external or internal. And with this method, we're going to model the fluid on both sides. Both in the direct method and the indirect boundary element method, we look for a so-called fundamental solution. And that's the acoustic pressure field in free space that's caused by a point source of noise. That is found from a solution of the Helmholtz equation shown here, and we use psi for the specific solution to this non-homogeneous problem. Non-homogeneous meaning that we have this Dirac delta function on the right side. Now that's a three-dimensional Dirac delta function which has a unit magnitude in a three-dimensional sense, that if you integrate that source strength over all three dimensions you end up with unity. So the fundamental solution then, which is found and shown below here, is the response to this small point source of sound, and has the interesting characteristics shown. It's exponential. It's a complex exponential which gives it a wavy character at any instant of time as you move away from that source. And then it has a diminishing magnitude going like 1 over the radial distance between the source and the data recovery point. So you get this outgoing spherical wave. We have removed the time dependence through the Helmholtz equation. The time dependence is shown only through this k value, this wave number. And so this captures pretty much the spatial content of the problem in acoustics. When we bring back in the time dependence, it's in the form of an exponential e to the I omega t, and we could then say that the pressure field shown below here is a function of both space and time, is the fundamental solution in space times the exponential function in time. Now let's develop the equations for the acoustic fields, both the external field and the internal field to this vibrating body. We'll do this in a way that's similar to the direct boundary element method. We see that the Helmholtz equation applies in the three-dimensional space everywhere but at the exact location of the source. On the other hand, the fundamental solution was defined with this equation shown below here that gives the source strength on the right-hand side. So what we're going to do is use the homogeneous Helmholtz equation as a weight in the problem, and we'll use the left side on some of the terms to be considered and the right side on others. The fact that those are equivalent then should allow us to do a volume integration with some special care taken at the point where the viewing point and the source point are identical. That occupies quite a bit of interest in the classical literature for this sort of an approach. So below now you see the description of the Helmholtz equation for the fundamental solution that I'll outline with the wiggly line here. And then we're going to pre-multiply first by the k squared p term in two locations, and on the other hand by the del squared p in this third location. Since those terms are equal out in the free space, then we don't need to distinguish between them, and we just use them alternatively as weights. In a minute we'll integrate over that volume. First I do a little bit of rearrangement here. We cancel the wave number and put the equation in the form shown below. Let's integrate the equation we've just developed, equation 3, over an acoustic volume of interest. The equation is shown here, and I've only written it once. It could be applied either to an interior cavity region, shown below in blue, or it could be applied to an exterior radiation region, shown in red. Now the outer boundary of that region goes to infinity and actually is an infinite surface located infinitely far away. So if we concern ourselves first with the exterior region, then the limits of this volume integration would include all the space between the surface of the vibrating body here, which is probably a hollow shell, and then the exterior infinite boundary. There are then three possibilities in evaluating this equation. And they have to do with whether the data recovery point, and I sometimes call this the viewing point, whether it is inside the region of interest, on the boundary of the region of interest, or on the in the other volume of interest. So outside the region that you really are integrating over. If the data recovery point happens to lie inside the region of interest, which for us would be the red region right now, then you're integrating a Dirac delta function in 3 dimensions over its entire non-zero domain, and you effectively get a unit value here ahead of this pressure at the data recovery point. On the other hand, if your data recovery point is in the interior, then you never integrate over the singularity where the delta function has non-zero values, and you get this 0 shown here. The intermediate case would be if the data recovery point were on the smooth boundary of the vibrating body, and then at some point you would basically be integrating a Dirac delta function over half of its domain, namely the half of the volumetric space lying on the side of the boundary that you're interested in. I could show that off to the side here with a quick sketch showing that you're integrating in some volume here, perhaps to the right, and the Dirac delta function takes its singular value right on that boundary and would have the effect of a propagation out into space, and then in that case you are only picking up half of the value of that singular source term there. Well, that's what leads to this 1/2 on the middle alternative. This same argument could be repeated for the interior cavity, in which the logic would flip in terms of whether you were inside your nice region or exterior to it. By choosing somewhat generic description on defining these positions, we find that the same discussion would hold. And in fact, there really are 6 alternatives involved here, all described in this one equation. 3 of those figured out from the data recovery point position, and then the other 2 permutations according to the limits on the volume integral. Before proceeding with our theory, I'd like to back up a bit and remind you about the significance of the gradient of pressure. We discussed this in an earlier lecture where we showed the momentum equation. Actually, if we think now of a component normal to a wall of the velocity and the pressure gradient, then we can see, once we realize that the velocity field is oscillatory in time with the exponential character, that the time derivative here brings out an I omega, which is shown in the figure here. And you have a relation between the normal gradient of pressure at a wall with the velocity component at the wall. Both are oscillatory, and there is some phase shift in time involved through the minus sign and the I. But generally speaking, you see that it's the pressure gradient that drives the velocity. In the indirect method, we're going to work with both sides of a given boundary. This is going to require us to use the volume integration for the field equation on either side of the boundary. Also, we'd like to change our problem into a set of variables that are differences in pressures and velocities on the 2 sides. Here's the first expression for a pressure jump, delta P, and it's defined as the difference in pressures between the two sides. Pressure is always positive when it pushes against a side. Secondly, we're going to have a quantity viewed as a single symbol here, an increment in the normal derivative of pressure. This is actually a velocity jump across that surface, and it has sign sense according to the normals to the surface. So this one is a little tricky then, and later when we get to some so-called multiple junction relations, the orientation of these normals and the positive sense of the velocity will have a sign character that we have to account for, but that's not too hard. So a pressure jump and a velocity jump are used rather than the original single variables. And this is what helps you deal then with the fluid on both sides of the surface. We're now going to use a volume integration on either side of a surface of interest. This is the Helmholtz equation that we previously showed. We will start out with the original form shown above here for the region 1 and below for the region 2. In each case, we know quite a bit about the terms. We know the fundamental solutions, so we can calculate these quantities that I will underline with waves. But we don't know the quantities shown that are pressures and gradients of pressure. We have several things to overcome. One is that we'd like to work with differences of pressures across the boundary and differences of the gradient of pressure, which is a velocity. Those variables are deal with the field variable P and its first derivative. We see that there are second derivatives here, and so this is clearly a candidate for one of the versions of integration by parts in vector form. So we'd like to have expressions that only involve first derivatives. Let's carry out the use of the Green's theorem and show the full set of terms that would occur in those two previous volumetric integrations. So I will show literally that these two terms do cancel, and likewise on the volume 2 these two terms cancel. That would be immediately claimed if you do use the symmetric form of Green's theorem. Now the normal to this surface for volume 1 is called N1, and it's shown positive outward to the lower right. Likewise, the normal to the second volume, N2, and its bounding surface is outward, shown upper left. Pressures are always positive when pushing, and so they both push against the surface. In our previous figure, after applying our vector theorem, we were left with a surface integral on either side of the vibrating surface. We don't have a contribution from infinity because of the Sommerfeld radiation condition, wherein we have a wave that's going outward only. We're not interested in an inward traveling wave, and its amplitude dies off sufficiently such that there's no contribution at infinity. So what were once two volumetric integrals on either side of the surface have now collapsed into surface integrals on that surface. And it's the same surface for both of our regions. Therefore, our integration variable ds is common on either of those two sides of the surface. The definition of the normal of the surface is different for the two volumes, and that just requires reconciling a minus sign to compare those two normals. So we're going to add the two equations, consider the surfaces to be the same in terms of their areas and area integration, but the n1 normal vector is negative of n2. because those were defined for volumes at a bounding surface with the positive sense away from the volume of interest. We will write N1 in terms of N2 arbitrarily, eliminating N1 and then bringing in the minus signs that are shown in red, as well as this subscripted N2 variable in our first integral term. On the right side, we will also add the non-homogeneous terms due to the Dirac delta functions. The integral terms simplify when one converts to a pressure difference and a difference in the gradient of pressure at the wall. So by defining this as a new variable and this as a new variable, we bring the equation down to a simpler form. I'll also comment again on the fact that we have only first derivatives involved here rather than second derivatives, and that was a result of our integration by parts. On the right side, we go through similar logic to what we did for a single volume integral. This time we're adding the results of two such integrals over a Dirac delta function, and we end up with these relations where you get either a unit value, a half value, or a zero value for one of the integrals, and the reverse holds for the other integral. And in all cases, it boils down to just the pressure at the data recovery point, interestingly. So you get quite a simplification now. The integral term on a surface and related to a pressure at a recovery point, regardless of where that recovery point is. We'll now use the notation that we've defined earlier for the jump in pressure and velocity across the surface. So here's our expression for pressure, and this is general. It would hold for any data recovery point in the either of the volumetric spaces. Our variables are the jump in pressure there, and then this term, which is to be viewed as a jump in velocity across the surface. We already know the fundamental solution and its derivatives because that's an analytical function, an exponential. It's easy to handle. So it requires a surface integral. I'll just temporarily here use the subscript a to remind you that that's a point on the boundary S, the common boundary to the two volumes that we originally studied. The unit normal now has to be uniformly directed on this surface either to one side or the other, and that's an arbitrary choice now because it really didn't matter which way you chose as your primary definition for the normal. I'll bring this equation back at the end of our lecture to show that it also is the way that you recover data away from the surface out on a viewing surface, either a plane, a sphere, or a cylindrical viewing surface. We're now ready to discretize the surface. We need to do this to do the integrations that we've spoken about. And we're going to use a boundary element approach. This means we need to characterize a surface by sets of quadrilaterals and triangles that are used to discretize with nodal coordinates that define the pressure field. The isoperimetric element approach is used. These elements are originally defined in some XYZ space, but then are mapped onto a two-dimensional space as zeta 1, zeta 2 space. Typically the quadrilaterals are mapped as shown on the right into a double unit square in the C1, C2 space. Then the total surface shown below is made up of a combination of such elements. Currently I'm showing you elements that only have node points at the vertices. These are sometimes called linear elements. They're lower order elements, and they usually suffice in acoustics, similar to heat conduction, where the equations are of lower order. They're second order differential equations and not as difficult as some of the structural equations that are perhaps fourth order equations in the plate and beam equations. So these simple elements are fine for us. To carry out the integration over the bounding surface that we're interested in, we're going to use the boundary element method. This is a way to discretize that surface with node points sprinkled around the surface. Then we'll use the shapes shown previously as connecting lines between those nodes. What's really important are the interpolating polynomials or shape functions that are used within each of the elements. Here I show the field variable pressure written as a function of the surface coordinates C1, C2. The shape function is given the symbol capital N, and then the nodal pressures are P. The superscript little m stands for the index then, and you have to sum over all of the nodes in a given element. We might say there are m, capital M, nodes in an element, and we have a scalar field here, which is pressure, so you only have one pressure variable per node. Now, in the isoperimetric theory, you also interpolate the sides of the elements, in other words, the geometry of the element. And that's given below here, and when you use the same shape functions to interpolate on the coordinates as you do on the field variable, then it's called isoperimetric theory. In the indirect method, we're going to use a variational approach to satisfy our field equations. And that integral approach using a functional will satisfy the same boundary conditions as the original differential equation formulation would have. These boundary conditions are shown as divided on this surface on the lower right, where you have one part of the region where the pressures are specified, and this would really be a pressure jump in our case. A second surface where we specify the velocities, and it's really a velocity jump. And then a third surface which an impedance boundary condition is provided on. That's a combination of pressures and velocities and has to be handled separately. We're now going to use that equation that we just found for recovering pressure at an arbitrary point r sub dr. It was a data recovery point. And we first will look at recovering pressures on the surface where pressure jump is specified. Now the idea here is that we're going to get n equations and n unknowns, and so we're going to put the place where we observe the pressure down on the surface where the pressure sources are, and hopefully permute our observation point to coincide with each of the sending points. So these integrals that we're to evaluate then are distinguished by where the data recovery point is in our case. And first of all, we're going to put it to lie on the blue crosshatched surface here where a pressure jump is specified. We find that the integration then, although your data recovery point is at this red spot, you have to still do the integration over the other three areas. And you find that the integration then depends on different quantities in those areas. Remember that you know the fundamental solution everywhere, so you know that part of these integrals. But you don't know these other quantities in general, and these are the unknown variables. I should use a different line here. Let me take a kind of a solid line for the unknown variables in each of these cases. So you involve here a jump in velocity here, and a jump in pressure here, and a jump in pressure here. The second case of interest is where your data recovery point would lie on a portion of the boundary where the velocities were prescribed, and that's shown here. And it's illustrated by the blue crosshatched area below. In this case, it's easier to deal with the derivative of the equation that we looked at previously, and it would be the time derivative equation. That will bring in the variables in the best form. We still have these known quantities on the various fundamental solution terms, and then we have these unknown quantities here. Now the integrations are starting to get to be fairly tough, but doable. In each case, we would do an isoparametric element mapping of the region in question, so you would ultimately discretize and have nodes that are the important points rather than surface integrals. The third region of interest is when you choose a data recovery point on the impedance specified boundary. And the impedance is a combination of a pressure and a velocity. So what we'll do is take our previous two equations and do a summation there to develop this equation shown on this figure. It would take you probably 10 or 20 minutes to sit down and actually do this. I've done it myself, and it's detailed, so I'm not going to go through it here. We're interested in this blue cross-hatched region, and this time you get a couple of terms up here related to a group of terms below. We still have the pattern of unknowns and knowns in a mixed way here, and we still know the fundamental solutions, so this becomes our third ingredient on getting the proper numbers of equations and unknowns. The third region that we discussed actually can be modified to include a possible fourth type of boundary condition, and that's where you have a wall that has both velocity and impedance conditions imposed at the same time. This would be like the roof of a car that had some kind of an acoustic treatment on it, a liner that was absorbing, say, and you knew from experiment what the surface velocities were, but you also know what the impedance of the liner is. So that can be handled as a special case by modifying the previous equation. Now, though, our job is to take those three regions that we discussed and to sum the results into a gigantic functional, which will be a scalar quantity. It will basically have energy units in that you're trying to put the different conditions on the same basis. Some people call this a Galerkin approach, so that in our case, if you have something that's pressure-like, you multiply it by velocity and then integrate over some relevant domain. On the other hand, if you have a velocity term, then you multiply it by pressure. And it's the product of pressure and velocity that has the dimensions of energy. So we will assemble this gigantic functional by taking our equation 6, which was defined over a domain where pressures were prescribed, and we multiply that by a velocity jump and then integrate over that domain. Secondly, we take the equation 7, which was with the surface where velocities were defined. It was basically a velocity condition. Multiply it by pressure jump and then integrate. The third equation that had to do with an impedance specified surface, we converted over into something more like a velocity condition, and therefore we multiply by a pressure jump, again getting something that's comparable to the other two equations. We then add all three equations and show the functional on the next figure. Not only do we add those three equations, but we first integrate over the relevant domain that each equation is defined on. So the first equation is integrated over the surface where pressures are defined, the second over the velocity defined surface, and the third over the impedance defined surface. And then those are the things that are added into this functional. This has a lot of terms, and again we know the fundamental solution psi, and so we're able to say that we understand all of these curly underlined terms. The unknowns are both the velocity jumps and the pressure jumps, both with subscripts A and B, and therefore there are 4 of these unknown functions at the present time within this functional. Then you create a variational statement which basically says that the variation of the functional is to be 0. And you get that by varying the functional, much as in a chain rule, by varying independently the dp's, the delta dp's, that is both the pressure and the velocity jumps, and whether at RA's or RB's. The final assembled sets of equations are illustrated in the next figure. We have a functional which represents a sort of system energy. It depends on the jump at the surface in pressure and in velocity. In mechanics, there are some rather general theorems, such as Hamilton's principle, from which other mechanical laws can be derived. And the general variational process here would be derivable from Hamilton's principle, say. I'll give some of the references on the title page to the general variational approach in acoustics. Usually you find classical people, the Lagranges, the Laplaces, Bernoullis involved in such energy approaches. Now we're going to take a surface and discretize it by placing nodal points in some regular pattern connected by our boundary elements. We'd like to say that if we know what's going on at those points, that then with our interpolation polynomials we know what's going on in the interior. And then at the end we'll show, of course, you can recover pressures at a remote point as well. Our numerical integration through boundary element methods will create a set of n equations in n unknowns. The form that we're showing here is after it's been reduced to a standard form where all the unknowns are in the g vector and all the knowns are in the f vector. Now, the g vector will indeed include jumps in velocity, delta dp, as well as jumps in pressure, delta p. And then the force terms over here derive from those prescribed boundary conditions on pressure, velocity, and so on. The matrix A is a symmetric matrix, which is helpful, and that's our boundary element matrix, often thought of as a stiffness in mechanical systems. The boundary element matrix for this method is fully populated, but it's symmetric. Compared to the single zone solutions using the direct method, the indirect method is quicker and requires less computer memory. That's because the solver exploits the symmetry of the boundary element matrix. Also, since the acoustic medium is felt on both sides of the boundary element, there's no distinction between an interior and an exterior radiation type of analysis. We're able now to work with thin fins, and there can be openings in the body. We can solve transmission loss problems. The indirect method is so powerful that it allows modeling some rather complicated geometries. And because of that, to get around 2 special situations, we need to apply so-called constraint equations. For instance, here you have a body made of 2 hollow cylinders with fluid both on the inside and outside of the cylinders. They're connected by this thin body here, a fin, and on the outside there are other fins. When you use the indirect boundary element, then the boundary element senses the fluid on both sides of its surface. Now, one problem that arises is at this free edge. Typically, we specify a velocity condition at this vibrating fin. But when you reach the free edge, you have to make sure that the pressure jump there is not artificially large. And it's common then to set a zero pressure jump right at that free edge of the plate-like body. That ensures then that the exterior fluid field understands that that is precisely the corner of the body, and there's no pressure jump allowed in the fluid over this infinitesimal distance, just off the end of the plate-like fin. It's related a bit to some of the conditions in fluid mechanics and aeronautics, say at the trailing edge of an airfoil, where you require a certain kind of continuity of the fluid behavior just as you leave the trailing edge of the airfoil. Now, a second situation has to do with these multiple connections where there would be an interior point of fluid near the connection and then an exterior point here and another exterior point here. We need to make sure that the pressure jumps that are used as variables make sense, such that as you go through a closed path here, you arrive back at the same pressure as you started with. So that's the so-called multiple connection condition. Let's look into these constraint conditions a little more carefully. First of all, for the zero pressure jump at the cut edge of a plate-like body, those nodes are pointed out by the red arrows. What you're really saying is that just off the edge of the plate into the fluid cannot support a jump in pressure because it's continuous fluid there. Of course, just inboard on the plate, you can support such a pressure difference. But the role of such a zero pressure jump then is to alert the Helmholtz equation to the fact that that's a cut edge. Now, unfortunately, this is not a very accurate mesh that I'm proposing here, because then the velocity conditions, which would be the normal conditions, are carried only on the interior nodes of that plate. It's actually better to have a thin layer of elements just inboard of the cut edge so that you get nearby nodes where you can have the velocity conditions prescribed. You might say that that node on the edge is thrown away for purposes of accurate pressure calculation, just to tell the equations where the edge is, and then the proper velocity conditions have to be prescribed at the remaining nodes. Now, the second constraint consideration has to do with the pressure jumps when you move around in a closed circle in a situation shown here. We have this hollow cylinder with fluid inside and outside. We have defined a normal. Let's suppose that it's outward on the cylinder, and arbitrarily, let's say it's to the right on the fin. Then, when you consider pressure jumps, you might start with your tension in the interior of the body here at some pressure then, close to the junction. The delta P1 would be the jump in pressure moving through this little arc, and it would be P2 minus P1. Then, as you look at the second pressure jump moving in this direction, then you would have P3 minus P2. Finally, moving in this way to get back home, the pressure jump there is actually P3 minus P1 because of the way the normal has been defined. Yet we want, when traveling in a closed circle like that, to end up with the same pressure that we started with. In other words, the three pressure jumps must add up to P0. That can be done with proper sign sense by putting a minus sign on the delta P3. And so this becomes the multiple connection constraint equation. Now, these are handled automatically in the commercial code Comet acoustics. After we've found our solution to the acoustic problem on the surface of the body, then we would naturally like to find acoustic pressures out in the field itself. Up till this point, we've only evaluated pressures on the surface. We've only needed to do that to develop the n equations in n unknowns, where we selectively set the data recovery point at each of the nodes in question on the surface. Once those are found, however, then you can use the same pressure expression as we had found earlier to recover pressures on a data recovery point that's off the surface. I'll repeat that expression here, and this time what we're doing basically is concentrating attention on a data recovery point at some distance from the surface, perhaps external as shown, and we're using known information now at each of the nodes around the surface of the body to collect the information in this integral. This is actually a forward process in an analytical sense. You don't have to invert any relations. And so is moderately inexpensive in that sense. On the other hand, if you have a viewing surface such as a sphere surrounding the vibrating body, you have a lot of points in question, and so there is a lot of calculation to be done. So this data recovery phase is not trivial, but on the other hand doesn't involve inversion of large matrices either. Our next lecture will give us some examples of the indirect boundary element method.